Hello, my name is Leo. Today we're going to talk about number systems. Number system or system of numeration or numeral system is a way to express numbers. We have also number sets like natural, rational, real, complex numbers and so on, but they're only part of number systems. The main two types of number systems are non-positional, which has sign value notation, and positional with place value notation. The most famous non-positional system is the Roman number system. In this table we can see the basic Roman numbers with their Hindu-Arabic equivalents we usually use to write numbers in everyday life. Here are these two rules we use to express more complex Roman numbers. These are rules of addition and of subtraction. Rule of addition. We have example I equals to 1, which is then 1 plus 1 equal to 2. XII is this x, which is 10 plus 3 i's is equal to 13. Subtraction rule only applies when we should write 4 exactly same digits in a row, but it is forbidden in Roman number system because the maximum of the same numbers digits in a row is 3. So for example, 4 isn't I, but it is IV, which is 5 minus 1 equal to 4. We see that the first digit is subtracted from the second one of the number. And the similar case is in this second example. And the biggest number we can possibly write in Roman number system using these rules is 3999. You can see here. Positional system is today's most acceptable and most used number systems. The most important by positional system is its base. So positional system is defined by base, which is any natural number. And position is particular digit placed in a number, which is based on some nth power, where n is natural number. We have 4 basic positional systems. Decimal, which is today's most used positional system in everyday life. And then binary, octal and hexadecimal, which are used mainly to represent computer data. Decimal system is positional system with base 10 and with 10 digits from 0 to 9, including them. We can see it is the same number of the base and the number of digits. We have this example of decimal number 432, and each of these digits has its place, its position. 2 is on position of ones. 3 is on position of tens, 4 is on position of hundreds, and so on. And these ones are actually 10 on the 0th power, which is 1. Tens are actually 10 on the first power, which is 10. Hundreds are 10 on the second power, which is 100, and so on. And here we have these zeros in front of the number because we can put them as much as we can. They go to infinity. So this 432 as decimal number we present in this form. We put in subscript this 10 in brackets as a base of this positional system. And we have now 4 times 10 squared plus 3 times 10 on the first power plus 2 times 10 on the 0th power is 400 plus 30 plus 2, which is equal to 432. Binary system is positional system with base 2 and 2 digits, 0 and 1. And it's mainly used to represent computer data. As we can see in this table, this is the similar case as for decimal system, so each position has 2 on some power. We have here decimal binary number 101010, so it has a base of 2, which indicated in subscript, which is in this case something times 2 on some power. And now it is 16 plus 0 plus 4 plus 2 plus 0, which is 22 in decimal system. So here we have actually conversion from binary to decimal system. We can also do the inverse thing from decimal to binary in this way. First we have to draw a vertical line and then put a number we divide the decimal number by. In our case now is 2, because we have binary position system. So 2 we divide by 2, but it is integer division, so there is no fractional part, we discard it. The first step is to put that number onto the upper left part of this vertical line. So here we have 22, and now 22 divided by 2 is 11. We put 11 below this 22, and how much is the remainder? Well, 0. 22 divided by 11 by 2 is 11, and the remainder is 0. We put that remainder on the right side. Now 11 divided by 2 is 5, remainder is 1. 5 divided by 2 is 2, and remainder is 1. 2 divided by 2 is 1, remainder is 0. 1 divided by 2 is 0, and the remainder is 1. And if we watch, now this remainder side, this right side of vertical line, we have actually this now this binary number, which is from bottom upwards. So 1 0 1 1 0 is binary number as conversion from decimal number 22. Octal system is positional system with base 8 and 8 digits from 1 to 7, including these digits. Again, we have this table with positions, but here is 8 on some power. And we can also convert from binary to octal and from octal to binary. If we want to convert from binary to octal, then we have to group digits of binary number in groups of 3, going from the end to the beginning of number, because few digits in the beginning of number can remain. For example, here is 1 in this first group, so we have to put 2 zeros in front of 1, and now each of these groups represents some digit in octal system. 1 4 3. So 0 0 1 is 1. 1 0 0 is 4, and 0 1 1 is 3 in octal system. Now 1 4 3 is the number in octal system. And we can also do the inverse thing, as you can see here. Also, we can do a conversion from octal to decimal. And from decimal to octal, the steps are very similar. As you can see, here is presented this from decimal to octal. In this picture, again, we have to divide by some number, but in this case we divide by integer division by 8, because 8 is by base of octal system. And finally, hexadecimal system, which is positional system with base 16 and 16 digits. And here we have this table of digits in hexadecimal and numbers in decimal system. We can see that digits from 0 to 9, including them, are the equal, but when we go to 10 in decimal, it is A in hexadecimal. Then we have B, C, D, E, F for 11, 12, 13, 14, and 15. So it has 16 digits from 0 to 9 and from A to F. We have here conversion, similar thing as in octal system, conversion from binary to octal and octal to binary. Here we have binary to hexadecimal and hexadecimal to binary. Only here we have to group, in binary to hexadecimal conversion, we group digits by 4. So again, go from the end to the beginning of number. We remain with 1, 1, 1 in this first group, so we have to add 0 in front of these 3 ones in this first group of 4, and then each of these groups represents some digit in hexadecimal system, then put it together and we get hexadecimal number. And from hexadecimal to binary is inverse thing. And again, we can also convert from hexadecimal to 10, the base is 16, and from 10 to hexadecimal we divide by integer division by 16. The only thing we have to be aware of is that in this case we can get any remainder from 0 to 15 including, and in this case we've got, for example, 11, but digit 11 does not exist as one of the digits in hexadecimal system. It is actually B. So it is 76B, this number, in hexadecimal system. Now you've learned about number systems. Thanks for watching and stay with us.